Hello, my name is Akari Kojima. I'm presenting to you today from the Department of Chemistry. And today, I'd like to share with you a little bit about synthetic strategies towards heteroanionic oxytellurides. We're interested in doing this because heteroanionic compounds present an exciting opportunity to expand composition space for the discovery of novel materials and to strategically tune physical properties. Specifically, oxytellurides composed of oxide and telluride ions are promising candidates in many innovative green energy applications, such as transparent semiconductors and thermoelectrics. Relatively few oxytellurides have been reported, which is likely a result of synthetic challenges arising from volatility differences among reagents, therefore requiring alternatives to conventional inorganic synthetic methods. In this work, we present and compare synthetic strategies towards oxytellurides using two different solid-state methods, as well as characterizing structure and the thermal properties of synthesized oxytellurides using the powder X-ray diffraction and thermogravimetric analysis. To clarify, we categorize the two synthetic methods by the type of furnaces we use. One of the methods calls for the tube furnace, which synthesizes the products by heating the material under a gas flow. The other method uses a box furnace and synthesizes the product through heat in a static vacuum. In the tube furnace method, we place tellurium shot adjacent to one of the rare earth oxides in which both reagents are in an aluminum boat. Then we flowed hydrogen gas through the tube furnace before the heating process for a controlled atmosphere. After the controlled environment was established, we heated the furnace to 800 degrees Celsius and dwelled at that temperature for a few hours, and then the furnace was turned off to cool down to room temperature. After the furnace had cooled, the sample was removed. For the box furnace method, unlike the tube furnace, we used the fine shavings of the lanthanide rods and mechanically mixed in stoichiometric ratio with tellurium oxide in a gate mortar inside the glove box. After the sample was vacuum sealed and placed in the furnace is heated up to 850 degrees Celsius and dwells at that temperature for 48 hours and then cools back down to room temperature in about 3 days. It may already be evident, but there are some differences between the two methods we use to synthesize these products. The tube furnace method took less reaction time and the reagents are not air sensitive. However, we do have to take an extra step to remove tellurium from the end of the furnace with caution due to its toxicity. The box furnace has its disadvantages, since the reagents are air sensitive, which leads to impurities and has a slightly less percent yield compared to the tube furnace method. However, both methods successfully synthesize the desired oxytellurides. As for the products, we visibly observed different colors for each oxytellurides, and these products were observed in the powder X-ray diffraction. It was revealed that the structure of these oxytellurides is tetragonal and have alternating rare earth oxide and telluride layers. It was also revealed that all three samples have different thermal properties observed by the thermogravimetric analysis. The cerium oxytelluride oxidizes at lower temperature and eventually degrades. On the other hand, lanthanum and praseodymium oxytellurides oxidizes at higher temperature and does not degrade, but they also have unique patterns in their oxidations, in which the intermediate steps have not been identified yet. Moving forward, we now know that the two synthetic methods are successful in synthesizing lanthanum, cerium, and praseodymium oxytellurides, and we can apply these methods towards novel oxytellurides. We also have revealed structural characterization of the oxide and telluride layers and the thermal properties. With the observed unique thermal properties of these oxytellurides, we are currently investigating the unknown intermediate step suggested by the thermogravimetric analysis. Thank you so much for listening and have a great day.